During this lesson, we will be looking at the flight director system. We will see how information is displayed to the pilots, the components and inputs required for the system to work, and then look at the typical dual flight director system. The flight director system was originally designed to reduce a pilot's workload during the busy approach phase. To do this, the original artificial horizon was replaced by an attitude director indicator, ADI, which could display pitch and roll attitude commands provided by the flight director system. This helped reduce the number of instruments a pilot needed to scan during the approach. The flight director system uses one of two ways to display the information, either using twin bars forming crosshairs or a V-bar. Both demand pitch and/or roll inputs from either the pilot or the autopilot. With the twin bars, the vertical pointer displays roll commands, and the horizontal one displays pitch commands. The V pointer moves as a whole unit to command roll and/or pitch inputs. A fly up command is displayed like this. Fly down is displayed like this. Fly up and left looks like this. And when commands have been satisfied, the pointers are centralized like this. The attitude director indicators are being replaced by electronic primary flight displays, which are part of the modern electronic flight instrument system. They not only include the above indications, but also can display much more information. This includes indicated airspeed, pressure altitude, vertical speed tapes, and sometimes part of the navigation display. The flight mode annunciator is at the top of the display and indicates the modes and status of the flight director, autopilot, and autothrottle systems. The horizontal situation indicator is a gyromagnetic compass display which has added navigation information. On the mode control panel, we have a heading select switch which, when selected, allows the heading bug selector to select the heading for the flight director to follow. On some older aeroplanes, the heading bug selector is on the HSI. Also on the mode control panel is a course selector which allows a course to be selected for the flight director to follow when in VOR lock, which we will look at in the next lesson on flight director modes of operation. We have already discussed the displays used by the flight director system. Now let's look at the components that provide the information to those displays. The heart of the system is the flight director computer, which gathers and processes the information. Between the computer and the displays is an amplifier or symbol generator. The amplifier will amplify the signals so they can drive motors in the displays. This is used on older systems. The symbol generator generates symbols which are then displayed on the primary flight or navigation displays. In older aeroplanes, there are analog inputs from the air data computer and vertical gyro. The signals are converted via a digital converter into a digital output so that modern displays and autopilots can be used. In more modern aeroplanes, the vertical gyro is replaced by an inertial navigation system or inertial reference system, as they have much more sensitive gyros. The flight director system also requires inputs from the VOR ILS systems to enable it to display the aeroplane's position in relation to these navigation aids. The flight director also needs to know the aeroplane's height above ground, and therefore has an input from the radio altimeter. The flight director system needs to know heading information, which in more modern aeroplanes is supplied by the inertial navigation or inertial reference system units, but in older aeroplanes was supplied by a gyro compass. In addition, we require a means of inputting information into the flight director system, and for that we have mode controllers, or a mode control panel. We will look at this in more detail during the next lesson on flight director modes of operation. To be able to operate the system successfully, crews need to know which mode the flight director is operating in, and so we have flight mode annunciators, normally displayed on the top of the primary flight display, or separate mode annunciators on the pilot's panels for analog displays. We will take a closer look at the flight mode annunciators. These are vital to indicate to pilots the modes of operation of the flight directors and autopilot in roll and pitch, as well as the autothrottle mode and status of the autopilot, including automatic landing capacity. On older generation aeroplanes, the indicators turn amber when the system is armed, and green when the mode has been captured. With an aeroplane equipped with a primary flight display, armed modes are displayed in white and shown on the second line. When the system has captured the mode selected, it changes to green, moves to the top line of the display, and for 10 seconds has a green box around it. Most modern aeroplanes are fitted with at least a dual flight director system. This allows for redundancy. The systems are also compared by a flight director comparator. The flight director comparator compares the output from both flight directors, and if a difference is found, the flight director bars will be removed, and the crew will then have to rely on raw data. When both flight directors are being used without the autopilot, then the one that was selected first becomes the master. This is indicated on the mode control panel. The flight director modes selected are controlled by the master flight director and are displayed on both primary flight display flight mode annunciators. Having two flight director systems also means if one system should fail, then as long as the display equipment is serviceable, both can display the remaining flight director. This is normally achieved automatically in modern generation aeroplanes and by a switch selection in older aeroplanes. Flight director system failure indications are normally shown by flags primarily on the attitude director indicator or the primary flight display. Failures of the flight director computer, instrument amplifier, or the attitude direction indicator itself are displayed as an attitude or flight director flag. There are also failures of glide slope information, which are indicated by a red glide slope flag. Poor reception or loss of navigation information can be displayed in many ways. During this lesson, you have learned about the different types of displays and the main components of a flight director system. During this lesson, we will be looking at the different modes of operation of a flight director system. We will achieve this by following a typical flight from departure through climb, cruise, descent and approach until the aeroplane lands or goes around. Flight director modes generally are type-specific, and so we will concentrate on the most common ones in use today. The glide slope and course deviation indicators on the side and bottom of the attitude direction indicator display basic raw information, which is still available if the flight director system fails. This is information that has not been processed in any way, and in this example it simply shows how far left or right of track and how far above or below the glide slope the aeroplane is. If we look at an aeroplane that is intercepting a desired navigational track using only raw data, we will see that the aeroplane fails to anticipate approaching the track. So the aeroplane flies through the track and then has to continue the turn to intercept the desired track from the opposite side. A flight director computer takes this same raw information but processes it, working out the rate of change of deviation. This additional data allows the system to anticipate approaching the required horizontal or vertical flight path, and therefore it can adjust the amount of roll or pitch input so that the aeroplane smoothly intercepts the flight path and does not fly through it. The flight director adjusts the flight director bars, which can then either be followed by the pilot or, if engaged, the autopilot. The flight director system has the aircraft performance parameters stored in its database, and with the input from the air data computer, it will never command a maneuver which could overstress the aircraft. Before we look at the departure, let us look at the instruments we will be using to set and display the flight director information. Firstly, to set the information onto the flight director system, we have the mode control panel and the flight management system. The flight management system affects lateral navigation, LNAV, and vertical navigation, VNAV. These are selectable pre-programmed routes and vertical paths for the flight director system to follow, although for the majority of this lesson we will be concentrating on the mode control panel inputs. To display the flight director information, we have the primary flight display and the navigation display. The only other piece of equipment we will look at briefly is the VOR navigation selectors, as they tune the required frequencies that the flight directors will follow when VOR lock is selected on the mode control panel and a course is set on the course selector knob. As part of the pre-departure planning, the crew will complete the necessary calculations to work out departure speeds and initial climb angle. The V2 speed will be set on the mode control panel. They will also find out the departure procedure, which will include maintaining runway heading, which in this instance is 010. As well as that, there will be a track to follow, which in our case is the 161° radial out of Oxford for the Botley interchange, and then the 180° radial to Compton. To achieve this, the crew requires Oxford's and Compton's frequencies to input into the navigation equipment. Next, we need to set these frequencies and the courses to follow on the mode control panel, along with the 4 locks selector. Finally, the crew will be given an altitude or flight level to climb to, and this will be set on the mode control panel and shown in magenta on the flight mode annunciator. During departure, with the flight directors selected on, the crew have 2 methods of displaying a pitch demand on the primary flight display. Firstly, they can bias the pitch demand manually to a pre-calculated setting, which is displayed on the primary flight display. This gives the pilot an initial body angle to aim for after rotation. The other way is by selecting Takeoff Go-Around on switches on the throttles. This positions the pitch bar to command the initial body angle on rotation, and we are informed of this on the flight mode annunciators. After rotation, the flight director will alter the pitch command to maintain the best climb angle, until the indicated airspeed reaches the mode control panel speed, plus 20 knots, and the crew will also select Heading Select to command the roll bar to maintain the selected heading. The pitch command will remain this way until another pitch mode is selected, and we will use vertical speed. This selects the vertical speed we wish the aeroplane to climb at. In this case, 1500 feet per minute has been selected, which the flight director then commands. As the aeroplane reaches the mode control panel selected altitude, it will command a level altitude, and once level, the crew would then select altitude hold to maintain the desired altitude. Next, the pilot will be given a heading to intercept the course for Botley from air traffic control, which he will select on the mode control panel. The flight director will then command a roll angle to turn the aeroplane to this heading, which is known as Heading Select, and the pilot will then also select Forelock in anticipation of intercepting the selected course. As the aeroplane approaches the selected course, the flight director will automatically command a left turn to intercept this course, which is known as forelock control. The other way to set up lateral navigation is by using LNAV, which utilizes the Airways Track database in the flight management system. The flight director computer, using a combination of inertial navigation and global positioning systems, and the selected track from the flight management system, sends commands to the primary flight display, so the pilot can follow the selected track. This system can be used all the way, from pre-departure until arrival at the destination. LNAV mode is displayed on the flight mode annunciator in green, with the actual track being displayed as a magenta line on the navigation display. During the climb, cruise and descent phases of flight, most mode changes will be in pitch. From departure, we were in takeoff go-around, vertical speed, and then altitude hold. For the next stage, we will be climbing to the final assigned altitude using level change. The flight director commands a pitch attitude to maintain the MCP selected speed, and the pilot selects a constant thrust. As the aeroplane approaches the desired height, the flight director commands a level off attitude, and if the pilot did nothing else but level off, the aeroplane would then accelerate, so he also has to decrease the power available. He would also select altitude hold again to accurately maintain the desired altitude. The other means of controlling the vertical profile is by using a mode called VNAV, which has various pre-programmed climb and descent profile databases stored in the flight management system. As the descent phase is commenced, the pilot will select the cleared flight level or altitude on the mode control panel and select level change. The flight director will then command a descent on the pitch bar. The pilot will reduce power to maintain the selected speed, and as the aeroplane approaches the selected altitude, the flight director will command a level off attitude. The pilot will again have to increase power to maintain the desired indicated airspeed, and select altitude hold to maintain the desired height more accurately. As the aeroplane reaches its destination airfield, the pilot is normally given radar vectors to intercept the instrument landing system or ILS approach. To follow radar vectors, the crew will select Heading Select mode on the mode control panel, deselecting LNAV and putting the flight director back into Heading Select mode. As with the departure, the pilot will check the ILS plate for Southampton to obtain the course, and the ILS frequency will be set on NAV1. The course will be set on the mode control panel along with Vorlock. The flight director will automatically command the pilot to intercept and track the localizer. Once on the localizer, the pilot will select Approach, which arms the glide slope. On intercepting the glide slope, the flight director automatically switches from altitude holding to glide slope. The pilot will then follow the flight director pitch and roll commands until he reaches decision altitude, and then visually continue to land. If we look at a typical glide slope path of 3 degrees, it can be seen that a 1 degree deflection at 6 nautical miles would give a distance above or below the glide slope of 608 feet. So the flight director can demand the maximum pitch change to try and get the aeroplane back on the glide slope. At half a nautical mile, the same 1 degree difference now only creates a height difference of 54 feet, and the demand from the flight director has to be reduced to between 1/3 and 1/2 of the previous full demand. So the flight director computed information must be modified as the approach progresses to reduce the commanded corrections. Most modern systems achieve this by knowing their actual height above ground from the radar altimeter, and restricting the demand as they get closer to the ground. Let us look at the go-around aspect, as land will be covered during the auto-land lesson. As the aeroplane approaches the runway, it will be under the direct control of the operating pilot, and if there is a need to overshoot, then takeoff go-around would be selected. On selecting takeoff go-around, the flight director pitch bar demands 10 degrees pitch up, and the engines are accelerated to take off go-around thrust. Once the aeroplane is at a safe altitude, the crew will then talk to air traffic control for radar vectors for another approach. The vital information to take away from today's lesson is that the flight director takes the raw information and provides either the pilots or the autopilot with computed information. This is derived from the rate of change of deviation and displayed as command bars on the primary flight display. During an approach, the flight director computed information must be modified as the approach progresses to reduce the commanded corrections. In this lesson, we will look at the reason autopilots were introduced, then show the typical closed-loop pilot control system, and compare it with the typical autopilot closed or inner-loop system. We will then look at the different types of autopilot, typical autopilot redundancy on modern airliners, and the EU OPS requirements. Autopilots evolved to relieve the pilot of the physical and mental effort required to fly the aeroplane manually over long periods of time. With the autopilot looking after the basic function of flying the aeroplane, it left the pilot to concentrate on other tasks, such as navigation and managing the aircraft systems. The autopilot will react more quickly to a disturbance, therefore making the aeroplane more comfortable to fly in, and allowing more accurate maintenance of heading and altitude. It takes a pilot a certain length of time to react to a disturbance, and then still further time to decide which control to move and in which direction, whereas an autopilot has corrected the disturbance in a fraction of the time taken by the pilot to react. To better understand how the autopilot controls the aeroplane, it is useful to analyse how the human pilot maintains, for example, wings level. To confirm if the aeroplane is level, you need an external reference, and this can be either looking outside at the horizon or inside at the artificial horizon or attitude indicator. As we can see, the wings are level and no input is required. In the event that a gust displaces the right wing upwards, the change in attitude will be noticed by you. By looking at your reference value, you will be able to mentally assess the rate and magnitude of the displacement. That will then allow you to mentally calculate the correction required to bring the aircraft back to wings level, and apply that correction to the controls. Having made the correction, you can see the aeroplane moving back towards wings level. When the aircraft is back to the required attitude, the control input can now be removed, and the controls set to neutral. This process can be referred to as a control loop, following a sequence of continuous events. Detection of a change from the required attitude, calculation of the correction required, applying that correction into the flying controls, checking the response of the aircraft, and removing the control input when the required correction has been achieved. This is also referred to as a closed-loop control system, as it has feedback. In this case, the feedback is aerodynamic, the aircraft letting the pilot know that it is responding to the flight control input. Now we will replace the human pilot with some components that will follow the same process that you did. Firstly, an attitude sensor or rate gyro sensitive in one axis only, that will detect any disturbance of the aircraft in roll. Attached to the rate gyro is a transducer, which is a device to convert the mechanical movement of the rate gyro into an electrical signal that can be processed. This is a rate signal. The signal is compared in the flight control computer with an attitude reference signal of known value representing wings level. When these two signals are compared, the difference between them is calculated and an error signal is produced, which is in proportion to the displacement of the aircraft away from its wings level value. With this information, the computer can then calculate and produce an electrical signal proportional to the corrective action required, a command signal. The signal is then sent to a servo motor, which converts the electrical signal into a mechanical movement to move the flight controls, again in proportion to the command signal. The control surfaces will move, and the aircraft will respond to return back to wings level. The aerodynamic feedback repositions the gyro, and when the aircraft is back to wings level, the control surfaces are moved back to a neutral position to maintain the stabilized attitude. This control loop is referred to as an inner loop. It is a closed-loop control system that will control the aircraft about its center of gravity. In this basic form, it is only capable of enhancing the stability of the aircraft. It can also be referred to as inner loop stability or stability augmentation system. Flight guidance inputs will be looked at during the autopilot roll and pitch operation lessons. When the autopilot is switched on, it must be capable of monitoring itself for correct operation. If it fails, there must be a means to stop it controlling the aircraft. To achieve this, there is another feedback signal to let the flight control computer know what the servo motor has done. The computer is the brains of the system, and it is providing command signals to the servo motor. The feedback from the servo motor, referred to as rate and position feedback or control position feedback, is letting the computer know the mechanical movement of the servo motor. The computer can then instantly compare the movement of the servo motor with the command signal. And if there is any discrepancy, the computer will disengage the autopilot. The autopilot must not be allowed to maintain control if the servo motor is not following the correct commands. The inner loop seen here is also referred to as a servo mechanism. A servo mechanism is defined as a closed-loop control system where a small input is converted to a larger output in a strictly proportionate manner. The control column is still there, of course, but the autopilot takes control of the aircraft when it is engaged. When the autopilot is disengaged, the pilot takes control of the aeroplane manually. Closed-loop control systems having feedback are typical for this application. as the controls need to be centralized when the correction has been achieved. Open-loop systems are less common because they do not have feedback, so the control system would have no knowledge of the aircraft response to the control input. There is an inner loop for each axis of control, each having its own gyro, computer, servomotor, and control surface. Although in a modern autopilot, there may be one computer with separate channels of computation within it. Autopilots consist of either a single axis, a two-axis, or a three-axis system. A single-channel autopilot system will control the aeroplane in the roll axis only, using the ailerons. This is known as the primary axis, and at its most basic, provides lateral stability. A two-channel autopilot controls the aeroplane about the roll and pitch axes, using ailerons and elevators. The pitch axis is known as the secondary axis. A three-channel autopilot, which is standard on modern airliners, controls the aeroplane in all three axes: roll, pitch, and yaw. The yaw axis is known as the third or tertiary axis and is controlled by the rudder. The rudder channel is basically a stability channel and usually has interaction with the roll channel to assist in coordinated turns. Many multi-engine airliners have multiple three-axis autopilots to allow a measure of redundancy and to provide the ability to carry out an autoland. Each autopilot has its own three inner loops and will inevitably be powered from different generators. If the servo motors are hydraulic, they will be powered by different hydraulic systems. An operator shall not conduct single-pilot operations in IFR conditions, unless the aeroplane is equipped with an autopilot with at least altitude hold and heading mode. This means that the aircraft must have at least a two-axis or two-channel autopilot. During this lesson, you learned how the typical pilot controls an aeroplane and saw the components used in an autopilot in a loop to replicate the pilot's actions. You then learned about the single-channel autopilot, the two-channel autopilot, and three-channel autopilot. Finally, you saw the EU OPS requirements for autopilot systems. In this lesson, we will look at the different types of actuators used in autopilots, why automatic synchronization is provided, the necessary interlocks that have to be made before the autopilot will engage, and the reasons an autopilot will disengage. We will then look at the autopilot function auto trim and a non-autopilot trim function mac trim. Next, we will examine the autopilot interface. And finally, control wheel steering. We will start by looking at the autopilot's muscle, or how it moves the aeroplane's control surfaces. The autopilot achieves this by using either rotary or linear servo motors, of which there are two basic types. Servo motor actuators are either electrical or hydraulic, and can be connected in one of two ways with respect to the remainder of the flight controls. If the servo motor is connected in series, with the pilot's control and the control surface, then when the autopilot is engaged, the command from the autopilot servo will cause the control surface to move, but will not simultaneously move the control column. If the servo motor is connected in parallel with the pilot's controls and the control surface, then when the autopilot is engaged, the command from the autopilot servo will cause the control surface to move and will simultaneously move the control column through the mechanical control linkage. This will enable the pilot to have some visual confirmation of the autopilot command. Most aircraft with traditional mechanical controls will have their pitch and roll channels connected in parallel and their yaw channel connected in series. The yaw channel is likely to incorporate a yaw damper, which will continually counteract any Dutch roll tendency. This will be fully explained in another lesson. The series connection of the rudder will prevent continual small movements of the rudder pedals. Aircraft with fly-by-wire control systems have different arrangements, dependent upon the manufacturer. The autopilot cannot be engaged on the ground and used for the takeoff. The pilot will be ready to engage the autopilot at some point after the takeoff when the gear is retracted and the aircraft is in a steady climb. It may also be a standard operating procedure to fly the aircraft manually until the flaps are fully retracted. At this time, the pilot will have trimmed the controls to maintain the desired attitude without any continuous stick force. Within the flight control computer, there are synchronizing circuits which will continually synchronize the autopilot with the attitude and trim of the aircraft, so that at the point of autopilot engagement, the autopilot will take control of the aircraft smoothly, without jerking or the tendency for the control stick to be snatched from the pilot's hand. The autopilot will then maintain the attitude that existed at the time of engagement until further guidance commands are selected by the pilot. However, without synchronization, engaging the autopilot could jerk the control column, even wrenching it from the pilot's hands. Clearly, this is not an ideal situation, and serves to point out how important the automatic synchronization is. Before the autopilot can be engaged, a series of interlocks must be satisfied, and remain satisfied, to allow the engage interlock relay to hold the autopilot engage switch in the closed position. The first interlock consists of the autopilot disengage button, of which there are normally 3. There is one on each of the pilot's control columns, and one on the main control panel. The autopilot needs electrical power, and therefore has a power monitor interlock. The rate gyro that senses flight attitude disturbances must have a valid signal, and the autopilot computer and the servo motor must have successfully passed their self-tests. The autopilot also requires hydraulic pressure to be able to move the flying controls. Finally, the pilot needs to select the autopilot to engage. The autopilot will disengage if any of the previously mentioned interlocks open. In addition to the interlocks, attempting to select a second autopilot to engage will cause the first one to disengage, unless approach is selected. The autopilot will also disengage if the pitch auto trim system is either operated by the pilot or the system fails. This is covered later in this lesson. When an autopilot disengages, either by operation of one of the switches or for any fault, there will be visual and oral warnings. When the autopilot is engaged, it has to be capable of continually trimming the aircraft in pitch to account for variations of the centre of gravity, configuration and speed. If this did not happen out of trim, forces would be felt on the servo motor, and at the point of autopilot disengagement, a pitch input would occur, causing the control column to be snatched or jerked. To allow for this, an automatic trim or auto-trim system is fitted to continually remove any out-of-trim forces in pitch when the autopilot is engaged. When the pilot is flying the aircraft with the autopilot disengaged, he will trim the aircraft manually. Fly-by-wire aircraft have a full-time auto-trim system that operates in autopilot and manual control. Most airliners have a trimmable horizontal stabilizer and elevator combination for pitch trim and control. If the auto-trim system fails, the autopilot will not remain engaged. It cannot be allowed to control the aircraft if it cannot trim in pitch. If the pilot operates the manual pitch trim when the autopilot is engaged, the autopilot will disengage. Aircraft that fly at high subsonic or transonic speeds may suffer from Mach tuck or tuck under. This is a nose-down pitching moment caused by the rearward movement of the centre of pressure at those speeds. A Mach trim system is provided to counteract Mach tuck. It is independent of the autopilot and is switched on for the whole flight, but will only have an input into the controls to counter Mach tuck when the aircraft encounters the onset of the necessary speed range. On the glare shield is the mode control panel, which allows selections for the autopilot, flight director, and auto throttle. The mode control panel is easily accessible to both pilots. To engage the autopilot, the Engage button for the selected autopilot is pressed. If the interlocks are made, the autopilot will engage and a light in the button will illuminate to signify engagement. There will also be an indication on the flight mode annunciator. The flight mode annunciator, FMA, forms part of the primary flight display, PFD, along with displays of airspeed, attitude, altitude, vertical speed, and heading. The FMA usually occupies a strip across the top of the PFD, showing the AP engaged status, pitch and roll armed and engaged modes, and auto throttle engaged mode. Typically, engaged modes will be displayed in green, with armed modes in white. After the autopilot is engaged, the pilot can then select a pitch and roll guidance function as required. To disengage the autopilot, there is a disengage button on each control column and a disengage button on the mode control panel. When pressed, the control column buttons will disengage the autopilot and cause an aural and visual warning to occur. Which can be cancelled by pressing the button a second time. If the autopilot should disengage on its own, the same aural and visual warning will occur to alert the pilot. If the autopilot is engaged in control wheel steering mode, using the control wheel steering button on the MCP, then the pilot can use normal control forces on the control column to fly the aircraft with the autopilot engaged. The system achieves this by using a force transducer to convert a manual input to an electrical signal that the autopilot computer uses. The signal then goes through the autopilot's normal inner loop to move the control surface via the servo motor. Once the aeroplane achieves the new attitude, the pilot completes the feedback loop, releases the input, and the autopilot maintains this new stabilized attitude. During this lesson, you have learned how the autopilot moves the aircraft's control surfaces, the interlocks that have to be made before the autopilot will engage and remain engaged, and the reasons it will disconnect. Next, you are shown AutoTrim, which is an autopilot function, and MacTrim, which is not an autopilot function. And you studied the pilot-autopilot interface, the mode control panel. Finally, we considered the control wheel steering, which allows the pilot to use the control column to control the autopilot. In this lesson, you will learn about the outer loop controls used by the autopilot to control the aeroplane about the primary or roll axis. Included in this will be heading select and hold, VOR localizer interception and tracking, and lateral navigation known as LNAV. To use the guidance functions of the autopilot for long-term navigation and speed control, the autopilot needs to have current navigation and air data information fed into the computer. When the respective pitch or roll command mode is engaged, the computer couples the target value with the current value to generate a steering command to the inner loop. The following systems or components provide continuous inputs to the flight control computers: the Central Air Data Computer, CADC, supplies current airspeed, Mach, altitude, and vertical speed. Attitude reference is supplied by a vertical gyro, or an inertial navigation or inertial reference system. A magnetic heading reference system supplies current heading. ILS and VOR receivers supply radio navigation steering information. The flight management system supplies computer-generated route tracking for pitch and roll control of the autopilot, and speed and thrust commands for the autothrottle system. And finally, the radio altimeter supplies height information for autoland and autothrottle. Firstly, we will examine typical guidance functions for the roll channel. With Autopilot A in command mode, the flight mode annunciator will show command in green. Now any roll guidance function can be selected. The roll functions available are heading select and hold, forelock tracking, and lateral navigation or LNAV. If you wish to look at any of the enlarged images again, just click on them. Heading hold is a function that will cause the autopilot to maintain the current heading when pressed. If it is pressed during a turn, the autopilot will roll the aircraft wings level and maintain the heading it rolls out on. It is an easy way to interrupt a turn if required. This function is not available on the system we are demonstrating. Heading select is a very common function that allows the aircraft to fly to and maintain a heading selected with the heading selector. The heading selector is a rotary selector, which, when turned, will position a heading index or bug around the outer scale of the compass rose on the HSI, EHSI, or navigation display. It will also show the selected heading in the heading window above the heading selector. Also associated with the heading selector is a bank angle limiter, which may be rotated to manually select a limiting bank angle, typically from 5 to 30 degrees, in increments of 5 degrees. It may also have an auto position, when the flight control computer will calculate a limiting bank angle that is appropriate to the mode in use. For the example shown, the aircraft is currently on a heading of 090 degrees, and the heading selector is selected to 130 degrees, with a limiting bank angle selected to 30 degrees. When heading select mode is engaged by pressing the heading select button, the button will illuminate, and heading select will be the annunciation in the roll window of the flight mode annunciator in green to signify engaged. The computer will calculate the heading error and roll the aircraft into a right bank to maintain the limiting bank angle as the aircraft turns. As the heading error reduces, the computer will start to roll the aircraft back towards wings level. The aircraft rolls out on the selected heading of 130, with the heading bug aligned with the current heading on the compass display. The aircraft can be controlled by turning the heading selector left to turn left and right to turn right, as long as heading select mode is engaged. If the change in heading is small, the aircraft may not reach the limiting bank angle. The aircraft can automatically capture and track a VOR radial or a localizer beam by using the VOR selection. In this example, we will capture a VOR radial. Localizer mode will be described in the Autoland operation lesson. A VOR beacon is a ground-based radio navigation aid, which transmits information continually on a VHF frequency, having a range of around 150 nautical miles. VOR stands for VHF Omnidirectional Radio Range. The VOR receiver in the aircraft receives the transmission and converts the radio signal into range and bearing displays on the navigation display, or HSI. The course selector on the mode control panel allows a course to be selected with respect to the tuned VOR beacon for the pilot or the autopilot to intercept and track. There are two course selectors, one at each side of the mode control panel. The course selector on the left of the mode control panel is associated with a navigation receiver number 1 on the left of the glare shield or left of the center console, referred to as box 1. The right-hand course selector is associated with navigation receiver number 2, or box 2. In this aircraft, box 1 is coupled to autopilot A, and box 2 to autopilot B. In this example, we will allow the autopilot to capture and track a course of 090 degrees from a heading of 130 degrees and fly inbound towards the beacon along the 270 degree radial. When the frequency of the beacon has been tuned, a course of 090 degrees is selected on the course selector. This positions the course carriage on the HSI, EHSI, or navigation display. The deviation bar and scale show the angular deviation of the aircraft from the selected radial. When flying manually, the pilot would assess the rate of closure to the required radial by looking at the movement of the deviation bar and turn the aircraft at the appropriate time to intercept the radial. To enable the autopilot to automatically capture and track the radial, once the beacon has been tuned and the course selected, press the VOR button. The VOR lock button is illuminated, and VOR is displayed in white underneath the heading select annunciation to signify that the VOR mode is armed. As the aircraft closes towards the selected radial, the flight control computer is assessing the radial error rate. The autopilot also knows the angle through which it has to turn the aircraft, because it knows the current heading, 130 degrees, and it knows the course required, 090 degrees. The aircraft will reach the point of beam capture when the autopilot needs to start turning the aircraft. At this point, VOR mode becomes engaged, signified by the VOR annunciation moving up and turning green, to replace heading select as the engaged mode. The light in the heading select button will extinguish. The aircraft will now bank to the left and turn to intercept the selected radial as the radial error reduces. The aircraft will be rolled back wings level to maintain the magnetic course at the beacon, the roll channel of the autopilot being controlled by deviation signals from the radial. The heading selector takes no further part, but will be positioned by the pilot to the current heading when the aircraft is established on course. If it is required to fly over the top of the VOR beacon and continue outbound on the same course, then the aircraft must fly through an area overhead the beacon, known as the cone of confusion or cone of silence. In this area, the received signals are unmanageable, and the autopilot can no longer follow the selected radial. As the aircraft enters the cone of confusion, an over-station sensor causes the autopilot to temporarily maintain the current heading, typically for 2 minutes, while the aircraft transits through the cone of confusion. The autopilot can now track the 090 degree outbound radial until it is required to change course. The lateral navigation function of the autopilot allows the autopilot to follow a computer-generated flight path derived from the flight management system. The flight management computer has a database of navigation information, including standard approach and departure procedures, radio navigation aid information, and standard waypoints. A waypoint is a point on the surface of the Earth, designated by a latitude and longitude. Waypoints and VOR beacons are typically co-located to allow for either methods of navigation to be used across land. But of course a waypoint could also be a point over the ocean. The pilot can also manually enter any latitude and longitude to produce a unique waypoint. Waypoints can be collected together and saved in the flight management computer as a route with a sequence of as many as 120 waypoints. Standard routes are saved in the computer and can be accessed through the FMS Control Display Unit, CDU. When the required route has been identified from a list, the pilot can select it to activate it. It then becomes the active route and will be pictorially displayed on the EHSI or navigation display. The FMC database is updated on a 28-day cycle to ensure the latest amendments to any route or navigation information are being used. So if you are going to fly a scheduled flight from Stansted to Faro, you will be able to use a company standard route that had been entered by your operations department. You will be able to add a standard departure procedure for the departure runway and an approach procedure for the arrival runway. After takeoff, when the autopilot is engaged, the lateral navigation button can be pressed to engage lateral navigation mode. This will cause the autopilot to fly the aircraft sequentially through the active route series of waypoints. To navigate the aircraft, The flight management system needs the support of an inertial navigation or inertial reference system. The inertial navigation system knows where it is, and the flight management system knows where it is going. So between them, they can provide accurate long-term navigation through a sequence of waypoints, flying the aircraft along great circle tracks, which give the shortest distance between 2 points on a sphere. The advantage being that the system is self-contained and requires no information from outside the aircraft. It can, however, use information from outside the aircraft to check and update its position. The flight management system can auto-tune a pair of VOR beacons and use the distance from each to determine position, or use a satellite positioning system input. During this lesson, you have learned about the role modes of the Autofligth system, including heading select and hold, forelock, and lateral navigation. In this lesson, you will learn about the pitch or secondary axis flight path modes used by the autopilot. In most modern airliners, there will be an auto-throttle system, which will operate in conjunction with the pitch channel of the autopilot to control climb, cruise, and descent functions. One of the following pitch functions can be engaged simultaneously with a roll mode: altitude hold, vertical speed hold, and altitude acquire, which engages automatically on the completion of a climb or descent. We will give a brief overview of a typical autothrottle system to appreciate the compatible modes of autopilot and autothrottle. When engaged, the autothrottle can maintain either a target speed or thrust value. The speed target could be an indicated airspeed or Mach number selectable by the pilot using the speed selector on the mode control panel, indicated in the speed window, and on the primary flight display speed tape. The flight management system can also command a speed target. The thrust target could be a value of N1 or engine pressure ratio, EPR, depending upon which has been designated the primary thrust setting parameter for that particular engine. The target thrust can be set manually by the pilot, or it can be calculated by the thrust computer based on standard thrust ratings for takeoff, climb, cruise, go-around, or continuous. Or, the flight management system can manage the thrust when it is controlling the vertical flight profile. The target thrust value and the active thrust rating can be seen on the engine indications on the electronic display or a separate indicator. The autothrottle is armed using the arm switch on the mode control panel. Then it can be engaged in either speed or thrust mode by selecting the respective button, also on the mode control panel. The engaged mode will be shown in green on the flight mode annunciator. The autothrottle is disengaged by pressing a disengage button on the outer part of the throttle levers. There may also be take-off go-around switches on the throttle levers, which will cause the autothrottle to engage in take-off or go-around mode when pressed. On the ground, take-off thrust will be the target, and during the approach, go-around thrust will be the target. It would be normal for this type of aircraft to use the autothrottle to manage the thrust for the takeoff, climb, cruise, descent, and approach, up to the point the pilot takes control for a visual landing. If an auto-land is being carried out, then the autothrottle will remain engaged up to the point of touchdown. Prior to takeoff, it will be normal for the pilot to select a speed in the speed window appropriate to the takeoff. Typically, this is V2, or takeoff safety speed, plus 10 to 20 knots. Also, an altitude will be selected using the altitude selector appropriate to the departure clearance. In this example, we have set the speed window to 170 knots and the altitude window to 5,000 feet. Selecting an altitude in this window will arm the altitude alerting system and cause the thrust computer to calculate a climb thrust value based on the altitude change. The selected altitude is also shown at the top of the altitude tape of the primary flight display. A typical climb profile would include a climb speed schedule. In this example, we will use 250 knots, 300 knots, Mach decimal 7. This means that after the takeoff, the aircraft will be accelerated to 250 knots and climb to 10,000 feet at that speed, as there is an air traffic control speed restriction below 10,000 feet. After 10,000 feet, the aircraft will be accelerated to 300 knots to continue the climb until Mach decimal 7 is reached. Then the climb will be continued at Mach decimal 7. Initially, the aircraft will be flown manually, with the autothrottle controlling the thrust up to 5,000 feet. Then the autopilot will be engaged. The takeoff thrust will be selected by the pilot, or calculated by the autothrottle computer or flight management system. The target thrust N1 or EPR is indicated by bugs on the N1 or EPR gauges. The autothrottle will be armed prior to the takeoff by lifting up the arm switch. After lining up for takeoff, the throttle levers will be moved manually to approximately 80 to 85% N2. And the autothrottle is engaged in thrust mode by pressing the toga switches, thrust or N1 being the annunciation in green on the flight mode annunciator. The autothrottle will now advance the levers until the takeoff thrust is achieved. After 60 knots, the autothrottle will hold the levers at that position to maintain the selected value and to prevent the system from chasing any slight variation in N1 or EPR during the takeoff. After takeoff, at 400 feet above ground level, the autothrottle N1 button is pressed, and the commanded thrust reverts from takeoff to climb, annunciated on the engine instrument display. The speed selector can be used to increase the reference speed to 250 knots. Shortly before reaching 5,000 feet, the altitude alert system will alert the pilot to the fact that the aircraft is approaching the altitude selected in the altitude window. The pilot will level the aircraft at 5,000 feet and select speed mode for the autothrottle. The pilot can maintain the altitude, while the autothrottle maintains the selected speed at 250 knots indicated airspeed. Autopilot A will now be engaged in command mode, and heading select will be the engaged function in role to maintain the heading. With the autothrottle maintaining the speed in speed mode, altitude hold can be engaged in pitch. When the altitude hold button is pressed, the light in the button illuminates, and Alt Hold is enunciated in green in the pitch window of the flight mode annunciator. The autopilot pitch channel will now maintain the altitude, with the autothrottle maintaining the speed. These two are referred to as compatible modes. Modern autopilots will not accept incompatible modes. For example, altitude hold. and N1 would be incompatible, as neither the autothrottle nor the pitch channel of the autopilot is maintaining the speed of the aircraft. The easy way to remember compatible modes is that at any point in time, with the autopilot and autothrottle engaged, either the autothrottle or the pitch channel of the autopilot must control the speed of the aircraft, this being either indicated airspeed or Mach. The only time this may not be true is during a go-around, using the autothrottle and autopilot. The altitude hold button can be pressed during a climb or descent to interrupt the climb or descent, to level the aircraft off if required. With the aircraft in altitude hold, we can now climb our aircraft to 30,000 feet. There are 3 ways to cause the autopilot to climb or descend the aircraft to a new altitude. We can use vertical speed mode, flight level change mode, or vertical navigation mode. Flight level change and vertical navigation modes will be looked at during the second lesson on autopilot pitch operation. So let's now look at vertical speed mode. The first action is to select the required altitude in the altitude window. This will arm the altitude alert system and also cause the autothrottle computer to calculate a value of climb thrust based on the altitude change. We are going to bypass the thrust computer and use vertical speed mode first. When the vertical speed button is pressed, the light in the button illuminates, and vertical speed becomes the annunciation in green in place of altitude hold. The light in the altitude hold button goes out. Once vertical speed mode has been engaged, the vertical speed window opens to display the current vertical speed of the aircraft. In this case, we are neither climbing nor descending, so plus and 4 zeros would be indicative of level flight. The thumb wheel can now be rotated to select the required vertical speed. Our target today is plus 1500 feet per minute. As soon as the thumb wheel is moved away from 0, the aircraft will pitch up to achieve the selected vertical speed. At the same time, the autothrottle will move the throttles forward to maintain the target speed of 250 knots. The aircraft will maintain 1500 feet per minute rate of climb at 250 knots. At any time during a climb using vertical speed mode, the vertical speed can be adjusted by moving the thumb wheel to increase or decrease the vertical speed. As the aircraft passes through 10,000 feet, the airspeed can be increased to 300 knots by selecting 300 in the speed window. The autothrottle will push the levers forward to increase and maintain the new target speed. Climbing at a constant indicated airspeed of 300 knots will cause the Mach number to progressively increase. When the Mach number reaches decimal 7, the changeover button on the mode control panel is pressed. This causes the speed window to now show the Mach number that existed at the time it was pressed, in this case Mach decimal 7. The aircraft will carry on climbing at 1500 feet per minute rate of climb and at Mach decimal 7. As the aircraft approaches the target altitude, the altitude alert system will alert the pilot with visual and oral indications. Shortly afterwards, the autopilot has to reduce the vertical speed of the aircraft to capture the target altitude. This maneuver is called altitude acquire, and will allow a smooth transition from a climb or descent to altitude hold. Altitude acquire is a transitionary mode which cannot be selected, but occurs automatically from a climb or descent to an altitude hold. This occurs at between 300 and 500 feet or so before the target altitude, dependent upon the vertical speed at the time. The higher the vertical speed, the sooner it will occur. At this point, altitude acquire becomes the engaged mode in pitch enunciated by altitude acquire, replacing vertical speed. As the aircraft levels off, the autothrottle moves the levers rearwards to maintain the selected speed of Mach 7. When the aircraft is level, altitude hold engages in pitch, and altitude hold will enunciate, replacing altitude acquire. The light in the altitude hold button will illuminate. Descending using vertical speed mode is the reverse of the climb. First, select a lower altitude in the window. Then select vertical speed. Using the thumb wheel, select a desired rate of descent. The pitch channel of the autopilot maintains the rate of descent, and the autothrottle maintains airspeed. The speed can be managed in the same way in the descent, going from Mach number to indicated airspeed, then a speed reduction at 10,000 feet. Altitude acquire and altitude hold will engage when the aircraft levels off. Care is required using this combination of vertical speed and speed hold to ensure that the values selected on the mode control panel are achievable, to prevent overspeeding or underspeeding if too high a vertical speed is selected. During this lesson, you have learned about the modes used in the pitch or secondary axis, including altitude hold, vertical speed mode, and altitude acquire. Level change and vertical navigation will be covered in the next lesson. In the previous lesson on autopilot pitch modes, we looked at altitude hold, vertical speed mode, and altitude acquire, which is an automatic mode enunciated on the primary flight display only. During this lesson, we will continue to look at the remaining autopilot pitch modes, including level change and vertical navigation. This time, we will carry out the same climb we did in the previous lesson, using flight level change mode. Starting again from 5,000 feet, select 30,000 feet on the altitude selector. Remember that it not only arms the altitude alerting system, but also initiates the calculation of a climb thrust value by the thrust computer based on the change in altitude. For this example, let us say that we are maintaining level flight and 250 knots using a thrust value of 85% N1, and that the thrust computer has calculated that 95% N1 is the required value for this climb. After selecting 30,000 feet, now press the Flight Level Change button. Flight Level Change mode engages, and Altitude Hold mode disengages, indicated by Flight Level Change speed being the enunciation in the Pitch Flight Mode Enunciator window. Simultaneously, the autothrottle will change from speed to thrust mode, indicated by N1 or thrust in the Flight Mode Enunciator. The autothrottle will now advance the throttles to give 95% N1. As the thrust increases, the speed will tend to increase, but you can see that the level change button is linked to the speed window of the mode control panel. So to prevent the speed from increasing, the aircraft will pitch up and start to climb. As the aircraft is climbing, the auto throttle maintains a constant value of thrust, and the pitch channel of the autopilot is maintaining the speed by making small adjustments to the pitch attitude. If you look at the pitch window of the flight mode annunciator, it is telling you what it is doing. Flight level change speed. The target speed can be seen at the top of the primary flight display speed tape. When the aircraft reaches 10,000 feet, the speed can be increased by turning the speed selector to 300 knots, and the aircraft will pitch down to cause the speed to increase. The thrust will remain constant. When the aircraft reaches the changeover altitude, where a constant Mach climb is required, the changeover button is pressed, and the speed display will change to Mach 7. As the aircraft approaches the target altitude, the altitude alert system will alert the pilot as before. Shortly afterwards, altitude acquire will engage in pitch, annunciated by altitude acquire replacing flight level change speed. Simultaneously, the autothrottle mode changes from thrust to speed, annunciated by a change from thrust or N1 to speed. As the aircraft levels off, the autothrottle moves the levers rearwards to maintain the selected speed of Mach 7. When the aircraft is level, altitude hold becomes the engaged mode in pitch, and altitude hold will annunciate, replacing altitude acquire. The light in the Alt-Hold button will illuminate. Descending using flight level change mode is the reverse of the climb. When an altitude lower than the current altitude is selected in the altitude window, the autothrottle computer will target idle thrust. When the flight level change button is pressed, the throttles drive all the way back to idle, with idle or thrust showing on the flight mode annunciator. The pitch mode will change from altitude hold to flight level change speed, and the pitch channel of the autopilot will pitch the nose down to maintain the mode control panel speed. The speed changes in the descent can be made in the same way as before, using the changeover button to change from Mach to indicated airspeed, and the speed selector to reduce speed as required. Remember that the pitch attitude will change to adjust the speed. Lastly, we will carry out the same climb using the vertical navigation function of the flight management system. As well as the navigation information, the flight management system also holds performance data for the engines and aircraft, and has the ability to provide vertical guidance for the aircraft throughout the whole flight profile. It can provide target values of indicated airspeed, Mach and thrust for optimum control regarding a selected performance mode. For example, economy climb, economy cruise, or long-range cruise. Performance calculations are produced when the flight management system is initialized by entering values of weight, route information, target altitude, and cost index. A cost index is a figure provided by the company which is entered by the flight crew to determine the optimum performance with respect to fuel burn and trip time. The default performance mode is economy, using the minimum fuel for the minimum flight time. The vertical guidance function controls the aircraft vertically within flight plan constraints, producing pitch commands to the flight control computer and thrust commands to the autothrottle. From 5,000 feet, we will select 30,000 feet in the altitude window and then press the vertical navigation button. Vertical navigation engages, shown by the annunciation VNAV speed on the flight mode annunciator. Simultaneously, the autothrottle changes from speed to thrust, annunciated as either N1 or thrust. The speed window of the mode control panel goes blank, or is replaced by 4 dashes, to let the pilot know that the flight management system is now commanding the speed, and there is no longer control of the speed from the mode control panel selector. The target speed is still shown at the top of the speed tape. The autothrottle pushes the levers forward to increase the thrust to the flight management system commanded value, and the pitch channel of the autopilot pitches the aircraft to maintain the target speed. As the aircraft climbs, the speed transition is automatically commanded at 10,000 feet, and an automatic changeover from speed to Mach occurs at the required point. As the aircraft approaches 30,000 feet, the aircraft will carry out the altitude acquire maneuver, but this time it is not annunciated. Instead, the pitch window will change to VNAV path, and the autothrottle will change back to speed. The pitch channel of the autopilot is now maintaining the altitude or vertical path derived from the flight management system. VNAV Alt will be displayed, while vertical navigation is maintaining a mode control panel altitude, if flight towards the vertical navigation profile is constrained by the mode control panel selection. For example, in this case, if the vertical navigation target altitude was 33,000 feet, with the mode control panel selected to 30,000 feet. For vertical navigation to control the descent path, there needs to be a defined end of descent waypoint with an associated altitude constraint. This will allow the flight management system computer to calculate the required top of descent point at which it needs to start the descent, so as to be at the correct altitude at the end of descent point. The economy profile is economy descent to 10,000 feet. Then, to reduce speed to 250 knots or below. The change from Mach to indicated airspeed hold during the descent is also automatic. Ideally, the computer will use idle thrust and optimum speed values, but these can be varied to take account of unforeseen wind conditions to keep the aircraft on the correct descent path. To use vertical navigation for the descent, select the descent altitude in the altitude window prior to reaching the top of descent point. The flight management system computer will then automatically engage VNAV speed from VNAV path at the top of descent point for the pitch channel, and thrust N1 or idle for the autothrottle. The throttles will move back to idle and allow the aircraft to deaccelerate to the descent speed if lower than the cruise speed. Then the pitch channel of the autopilot will pitch the aircraft down to maintain that speed with idle thrust. Changeover occurs automatically from Mach to indicated airspeed, as does speed reduction at 10,000 feet. At the required altitude, the aircraft will level off as the auto throttle takes back control of the speed, and the pitch channel of the autopilot maintains the altitude. The flight mode annunciator changes auto throttle to speed and pitch to VNAV path. When lateral navigation is used in conjunction with vertical navigation, fully automatic, performance-optimized guidance through a sequence of waypoints is achieved in azimuth, elevation, and velocity. Lateral navigation and vertical navigation can be used separately. During this lesson, you have learned about the remaining pitch modes of level change and vertical navigation. In this lesson, you will learn about the Autoland system, including the reason for Autoland, the required airfield facilities, and aircraft components. You will learn the difference between fail passive and fail operational autopilots, and then the definition of an alert height and the actions required. Finally, you will learn some background information on weather minima and the 3 categories used to define Autoland landing conditions. The most difficult phase of any flight is the approach to land. It requires the pilot to coordinate the aeroplane's flight attitude about all 3 axes, keep the aeroplane on the localizer and glide path, and reduce the airspeed and rate of descent as the runway is approached. This is difficult enough. However, if we now introduce poor visibility, then the pilot's workload is greatly increased, and the chances of him achieving a successful landing diminish. Even with the introduction of a single 3-channel autopilot, flying the approach as far as decision height, and assuming the pilot can see the runway, the chances of completing a successful landing vastly improve. However, the limiting factor is still the pilot. If he does not see the runway, he can't land and will have to go around. With a full Autoland system available on the aeroplane, and the required facilities at the arrival airfield, the autopilot system can carry out a landing with 0 visibility and total cloud cover. For an aircraft to be able to autoland, it requires automatic control, with a high degree of accuracy during the approach, flare, and touchdown phases. To achieve this, the arrival airfield must have an instrument landing system, or ILS, that is accurate enough for an autoland to take place. An instrument landing system is a short-range airfield navigation aid, comprising a localizer transmitter and a glide slope transmitter. There will also be an appropriate minimum standard of approach lighting, and there may also be marker beacons, providing distance from touchdown indications. As well as marker beacons, there may be distance measuring equipment, or DME range indication, associated with the ILS, to provide distance from the touchdown point. The localizer transmitter is positioned at the far end of the runway and provides lateral guidance to the runway threshold. It could be imagined as a short-range single-radial VHF omnidirectional range beacon. The glide slope transmitter is positioned at the near end of the runway and provides vertical guidance down to the threshold, typically following a 3-degree glide slope. The ILS frequency is tuned by selecting the very high frequency localizer frequency, and that automatically tunes the pair glide slope frequency in the aircraft receiver. The navigation instruments in the aircraft can show localizer and glide slope deviation so that the pilot can fly the aircraft manually along the localizer beam and down the glide slope if desired. This information can be coupled to the pitch and roll channels of the autopilot, so that the autopilot can follow the instrument landing system. The minimum requirements for an autoland system are 2 independent autopilots capable of following instrument landing system signals, 2 navigation systems capable of being tuned to the instrument landing system frequency and providing deviation signals to its own respective autopilot, and 2 independent radio altimeters to give accurate height above the ground to each autopilot. Fail passive or fail soft is defined as the ability of the system to withstand a failure without compromising passenger safety and without producing excessive deviations in the flight path, but removing its capability to complete an automatic landing. This is normally a 2 autopilot system and will be enunciated on the flight mode enunciator as LAN 2. If an autopilot fails, it cannot carry out an autoland. Fail operational or fail active is defined as the ability of a system to withstand a failure without compromising passenger safety and without producing excessive deviations in the flight path, but after a single failure can complete an automatic landing. This is normally a 3 autopilot system and will be enunciated on the flight mode enunciator as LAN 3. If an autopilot fails, an autoland can still be carried out, and the enunciation will change to LAN 2. Effectively, it is downgraded from being fail operational to fail passive. The alert height is a specific radio height, which is based on characteristics of the aircraft and its fail operational landing system. In simple terms, this means that should a failure occur of a required system above the alert height, the approach will be discontinued and a go-around executed. This is unless reversion to a higher decision height is possible, and decision height will be defined in the next scene. If a failure occurred below the alert height, it would be ignored, and the approach continued to complete the autoland. A precision approach and landing requires lateral and vertical guidance and minimum values of decision height and runway visual range. Decision height is a specified altitude or height at which a missed approach must be initiated if the required visual reference to continue the approach has not been established.
Minimums.
Runway visual range is the horizontal range along the runway that a pilot of an aircraft on the centerline can see the runway surface markings or lights delineating the centerline. ICAO low visibility operations are split into 3 categories, which are known as Category 1, Category 2 and Category 3. Category 1 is defined as a precision instrument approach and landing, with a decision height no lower than 200 feet and with a visibility of not less than 800 meters, or a runway visual range not less than 550 meters. The decision height is based on the barometric altimeter. Category 2 is defined as a precision instrument approach and landing, with a decision height lower than 200 feet, but not lower than 100 feet, and a runway visual range not less than 300 meters. The decision height is based on the radio altimeter. Category 3 is split into 3 further categories, with Category 3A being defined as a precision instrument approach and landing with a decision height lower than 100 feet and a runway visual range not less than 200 meters. The decision height for all three is based on the radio altimeter. Category 3B is defined as a precision instrument approach and landing with a decision height, if any, lower than 50 feet and a runway visual range between 75 and 200 meters. Category 3C is defined as to and along the surface of the runway and taxiways without external visual reference. During this lesson, you have learned the reason Autoland was introduced, the minimum components required, and the difference between fail passive and fail operational. During this lesson, you will see the Autoland sequence from the initial setup through the approach to final landing or go-around. During the approach phase of a flight, the crew will normally be under direct control of air traffic control and be provided with radar vectors and descent heights to intercept the final approach course. The aeroplane would normally be set up under the control of a single autopilot, with the auto throttle controlling the mode control panel indicated airspeed. The crew will select the flaps and gear as appropriate to the aircraft during the approach. The autopilot will not select flaps or gear. Altitude hold will maintain the mode control panel height, with heading select controlling the mode control panel heading. From the instrument approach procedure, the crew will obtain the instrument landing system or ILS frequency to set on the VHF navigation radios and the inbound course to set on the mode control panel courses. The other thing to take note of is the radio altitude indication in the bottom right-hand corner of both primary flight displays, as this triggers some of the changes during the approach. Approach control allows localizer and glide slope signals of an ILS to be coupled to the roll and pitch channels of the autopilot. Selecting the approach button arms the approach mode, and this is indicated on the flight mode annunciator by localizer and glide slope being the armed modes in roll and pitch. To engage approach, at least one VHF navigation receiver must be tuned and receiving an ILS frequency. The autopilot can then fly the aeroplane down to decision height. The correct course needs to be set on the mode control panel to be able to start the approach to decision height. With both VHF navigation receivers tuned to and receiving an ILS frequency, with the correct courses set on the mode control panel, then a full autoland can be carried out. Any time after approach has been accepted by the autopilot, the second autopilot can be engaged. In this case, Autopilot B is the only other autopilot available. This means it is a fail-passive system, as you cannot continue with an autoland approach should one of the autopilots fail. The second and/or third autopilots are now referred to as offline channels, as they are performing all of the same calculations as the first autopilot based on their inputs, and are sharing information with one another, cross-checking, to make sure they are in agreement. At this point, however, they are not yet controlling their servo motors, which is signified by the command annunciation remaining on the primary flight display. Localizer capture occurs in a similar fashion to VOR capture. At the point of beam capture, Heading Select mode is replaced by Localizer mode as the engaged mode in roll. Heading Select is replaced by Localizer on the flight mode annunciator. The aircraft will now turn onto and maintain the centerline of the localizer, with the roll channel of the autopilot controlled by localizer deviation signals to follow the localizer beam. As the aircraft approaches the glide slope, the beam is captured in a similar fashion. Altitude hold disengages, and glide slope becomes the engaged mode in pitch. The altitude hold annunciation is replaced by glide slope on the flight mode annunciator. The aircraft will now descend on the glide slope, while simultaneously following the localizer. It would be normal for the pilot to keep one hand on the control column and follow through with the autopilot, right up to the touchdown. Some aircraft may cause the rudder pedals to be connected in parallel at this time, so that the pilot can also follow through any yaw inputs with feet on the pedals. In this fashion, the pilot knows exactly what inputs the autopilot is making to the flight controls. When the aircraft reaches 1,500 feet radio altitude, the flight control computer checks that the localizer and glide slope beams are captured. All selected autopilots are now fully engaged, and this is shown by Land 2 or Land 3 being annunciated on the primary flight display. At the same time, the flare mode will be armed in the pitch channel, and, if available, rollout will be armed in the roll channel. At 300 to 400 feet radio altitude, the auto trim system stores a nose-up trim signal in preparation for flare mode. During the approach from about 1,500 feet, the yaw channel will compute the difference between the aeroplane's heading and its actual track across the ground. The runway alignment mode is armed at the same time as the flare mode, and engaged at less than 400 feet, dependent on type. At this point, the yaw channel causes the rudder to kick off any drift prior to touchdown, which aligns the aeroplane with the runway centerline. At 50 feet radio altitude, or 45 feet wheel height above the ground, flare mode is engaged, and the glide slope signal is disconnected. The rate of descent is reduced to approximately 2 feet per second. This is achieved by the radio altimeter controlling the flare to reduce the rate of reduction of the radio altitude. At the same time, a signal is sent to the autothrottle system to retard the throttles, so that they are at idle thrust as the aeroplane touches down. There are two reasons for this. Firstly, thrust is no longer required as the aircraft is flaring. Secondly, the thrust levers need to be at idle so that after the touchdown, the pilot can select reverse thrust. The autothrottle will not control the engines in reverse. Next in the sequence is as the aeroplane passes through a gear height of 5 feet, or 10 feet radio altitude, when the flare mode is disengaged. The aircraft will touch down firmly in the touchdown zone. A firm touchdown is required if the runway is wet, to allow the tyres to break through any standing water and make firm contact, to avoid the possibility of aquaplaning. The aeroplane then transitions into the touchdown and rollout mode, which causes the nose to be lowered and the speed brakes and auto brake to be applied if selected. When reverse thrust is applied by the crew, the autothrottles disengage. If the aircraft does not have rollout control or guidance as part of the autoland system, the autopilot will be disengaged at this point, and the rollout controlled manually. If the aircraft has rollout mode, then either shortly before or at the touchdown point, localizer mode will disengage and rollout will become the engaged mode in roll. Rollout control will now use the localizer deviation signal to feed steering commands into the rudder to keep the aircraft on the centerline. There may also be an interconnection between the rudder pedals and the nose wheel steering after the touchdown, which will allow a limited authority of the steering. This will allow the aircraft to maintain the centerline of the runway, even after the airspeed has fallen below the speed at which the rudder is effective. Some aircraft may use a runway guidance system, giving the pilot commands to move the rudder left or right to maintain the centerline. With rollout control, the autopilot will remain engaged until the pilot disengages it at some point during the rollout. When the aircraft is in an approach configuration, go-around mode is armed. Go-around mode can be an auto-throttle, flight director, or autopilot function. Let us assume, following the auto-land approach sequence given before, that at decision height the pilot decides to go around. This is achieved by pressing the Takeoff Go-Around switch, positioned on or near the throttles. When the Takeoff Go-Around switch is pressed, all of the auto-land functions are disengaged, and the autopilot reverts to single autopilot operation. The auto-throttle changes from speed to thrust mode. The pitch enunciation is Takeoff Go-Around, and the roll enunciation is Takeoff Go-Around. The throttles move forward to give the required go-around thrust. This figure is calculated by the thrust computer and is based on the aircraft achieving a target vertical speed, typically 2,000 feet per minute. Go-around thrust is not necessarily full thrust. On some aircraft types, pressing the Takeoff Go-Around switch a second time will advance the throttles to full thrust. The pitch channel of the autopilot pitches the aircraft up to achieve the pre-programmed vertical speed. The roll channel of the autopilot maintains the track that existed at the time the Takeoff Go-Around switches were pressed. The objective is to fly the aircraft up directly over the runway centerline. Go-around is a one-button operation to keep the aircraft away from any danger. As the aircraft climbs, the pilot will move the flap from a landing to a takeoff position and select the gear up. The autopilot will not operate the gear or flap. When the aircraft has passed 400 feet above ground level, any roll or pitch function of the autopilot can be engaged. Typically, heading select and vertical speed, or lateral navigation and vertical navigation, if a missed approach procedure is part of the active route. The pilot can then use the autopilot to reposition for another approach at the same airfield, or fly to an alternate airfield, whichever is appropriate. During this lesson, you have learnt the selections a crew makes during an auto-land approach, from approach to localizer and glide slope capture. Then, the radio altitude heights of 1,500 feet, 400 feet, 50 feet, 10 feet, and finally, landing and rollout. You also learn the sequence of events when the crew operated the Takeoff Go-Around switches.